All right, so I'm going to push this box along the table, same speed, same direction. All right? So, let's answer these questions. Again, same speed, same direction. Okay, number one, I'm exerting a force on the box, so why isn't it accelerating? Well, what's also acting on the box? Friction. So friction. Number two, what are the forces on the box? Draw the force diagram. And this is the important thing, right? You have to know how to draw force diagrams. And you'll see why. All right, so let's just say that me is this way, right? Here's the object, right? And so we'll call this the force of friction. Now, what else is there, though? Well, there's always weight. There's always weight, which is mg. And of course, there has to be the normal force, F sub n. So there you go. And by the way, I should tell you, I don't usually draw these things carefully. I mean, if I were to draw them carefully, here, let me draw them carefully. If I were to draw this really, really carefully, okay, look at it. It was moving at a constant speed, right? Constant velocity. And it was not accelerating this way, and it was not accelerating this way. So if I were to do this really, really carefully, this ought to be the same as that, same magnitude, and that ought to be the same as that. I mean, it's close. But look, you'll see later on, when you're drawing these force diagrams, you don't have to be careful. Just draw it, all right? Don't worry about the length. Just draw it, and you'll see why later on. Okay, keep going. I already answered this, right? I answered 3 and 4 already. So that equals that, magnitude. That equals that, magnitude. Because there's no acceleration either direction. All right, let's do the next one. Okay, let's do the next one. Where's the thing? Okay, now, what I want to do this time is, so I'm going to push it and then let it go. Okay. All right, so after I am, all right, so everybody saw what happened, right? So I pushed it, let it go, it slowed down, then it stopped. So after I am no longer touching the box, and before it stops moving, what are the forces on the box? Well, look at, I'm no longer touching it, so you can't include me in the forces, right? What's the only horizontal force acting on the box? Just friction. So let's do it. So let's say that the velocity is this way, right? So there's always the weight, right? And there's always the normal. But what we care about is the friction. Okay. All right. Now, there's no longer any me because I'm not touching the box anymore. Right? So there's normal, weight, and the force of friction. And again, velocity is this way, force of friction is that way, because the force of friction slows things down. Okay, compare the magnitude of the vertical forces. That equals that. No kidding, because there's no acceleration this way. In what direction is the velocity? That way. And, okay, 4. In what direction does the acceleration vector point? Well, look, the force is this way. We know that F vector equals ma vector. So the force and the acceleration have to have the same direction. So A points in that direction. Now, this makes total sense. Remember a long time ago we learned if the velocity and the acceleration have opposite signs or opposite directions, the object slows down. Well, that's what we just saw, right? The object was slowing down. So the acceleration has to have an opposite sign to the velocity. So that's good. It all makes sense. Okay, now, look. You have to be able to draw force diagrams correctly. So all we're going to do now is practice. So I don't want you to solve the problem. Just draw the force diagram. So everybody read that and pause your video and then draw the force diagram. And don't cheat. You have to be able to do this. Okay, so we're back. All right, a student moves a box of books, attaching rope to it, 90 newtons at an angle 30 degrees with respect to the floor. So there's that 90 Newton force, 30 degrees relative to the floor. And blah, 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 blah. So all we care about are the forces, right? The forces. Okay. Now, it says there's friction. So we know we have to, so it's not on ice, right? So we have to include friction. All right, so here's the force, 90 newtons. Here's friction, right? Friction is opposite to, right? It's moving along the floor, right? It's moving along this way. So friction is opposite the direction of motion. Don't worry about the K, I'll get to that later. Here's the weight, and here's the normal. That's all. And obviously, okay, it's going this way. It's going to accelerate this way, so F net is that way. There's no acceleration this way. By the way, you can kind of figure out what we're going to do in a future chapter. We're going to take this vector, we're going to resolve it into an x piece and a y piece. Then we'll sum the y's and we'll sum the x's. But that's later. Okay, everybody read that and pause and draw the picture. Okay, so we're back. All right, a jet is flying with constant speed along a straight line at an angle of 30 degrees with the horizontal. What's with the 30 degrees? Okay, so we have something, right, like that. Okay, the plane, all right, so that's the thrust, right? The plane has a weight. So here's the weight. The weight always points towards the center of the Earth, straight down. So the weight is straight down. Okay, the plane has a weight. I don't care about the numbers, just W. The engines provide a thrust. Well, the thrust is along the direction of motion, right? It's too bad they use T, because we use T for tension, sorry. Right? In addition, there's a lift force and an air resistance force. Now, it says the lift is perpendicular to the velocity, so that means the lift is like that, right, where this is a right angle. And then what's the air resistance? Well, the air resistance is always opposite to the direction of motion, so that means that the air resistance is something like that. So here's my nice picture, okay? Close enough, huh? So thrust, lift is perpendicular, air resistance opposite to thrust, and then weight straight down. By the way, we're going to analyze this next chapter or somewhere along the line. Do you think we're going to tilt the coordinate system? Yeah. If we don't tilt the coordinate system, we're going to have to resolve 1, 2, 3 vectors. If we tilt the coordinate system, we only have to resolve the weight. Oh yeah, this is a good one. This is a good one. A block of mass M is held motionless by a rope on a frictionless, you like to see that, right? Frictionless inclined plane as shown. You suddenly cut the rope. Notice? Cut the rope. Find the block's acceleration. So all we want to do is draw the force diagram. So pause your video and draw it. All right, we're back. Now look, the rope has been cut. So the rope doesn't exert a force anymore. It's frictionless, so there's no friction. So what are the only forces? Well, there's always going to be weight, right? Weight is always going to go down, weight. I'm just writing weight equals mg because I want you to get it in your head. Weight equals mg. Now, what else? There's a surface, right? So there's always a normal force. Remember, what's normal mean? It means perpendicular. Perpendicular to the surface. So this time, the normal force points in that direction. Okay? It's perpendicular to the surface. This is a right angle. Okay? That's all. So here you go. That's all you have. So you have the weight straight down, the normal force perpendicular to the surface. Perpendicular to the surface. That's all there is. All right, let's see, that was number 5. Oh yeah. Okay, let's read this one. A block M1 rests upon a rough. What does rough mean? There's friction. M1 rests upon a rough incline, 30 degrees again. A massless cord is connected from this block over a massless and frictionless pulley to another block, M2. If the blocks are initially at rest, how long does it take for block 2 to reach the ground? So you're holding them steady, then you let go, and it goes like this. Now, before we do this, I want to explain something. So you notice it says a massless cord. What's a massless cord? Have you ever seen a massless cord before? No. Well, think of it like this. Think of a piece of fishing line. So I have a piece of fishing line this long. What's the mass of a piece of fishing line this long compared to like 2 kilograms and 2.2 kilograms? It's nothing, right? So I mean, there is no such thing as a massless cord, but basically what they're saying that the mass of the string is super insignificantly small compared to the masses in the problem. So again, fishing string, okay? Then it says a massless and frictionless pulley. Okay, so here's a pulley that you're going to use in lab. And I don't know how much it weighs. I should have weighed it, but it's really, really light. I mean, it's just plastic. Now, so again, the mass of this is nothing compared to 2.6 kilograms and 2.2 kilograms. It's nothing. So we can just say it's massless. Now let's talk about the frictionless thing. Okay, watch. Very exciting. I should have timed it. Oh, well. Now that's pretty good, wouldn't you say? I mean, if that's not frictionless, I mean, it's not frictionless, but it's really close to being frictionless. So that's all I'm saying is when they say massless cord or massless and frictionless pulley, it's just an approximation, but it's a really, really good approximation. By the way, later on we're going to learn how to deal with massive pulleys, and it's going to be real challenging. So just be grateful that we have massless pulleys right now. All right, draw the force diagrams. Why did I put an S here? Well, there's two objects, right? So if there's two objects, you've got to draw two force diagrams. So let's do it. So you pause your video and draw them. Okay, we're back. Okay, first let's do M1. So there's M1. Okay, what are the forces acting on M1? Well, there's always weight. Now here you have a rope pulling it up, so there's tension. Now it's going up incline, so there's a surface, so there has to be a normal force. By the way, you can call it whatever you want. I mean, you can. Some people just put an N. Some people put uppercase. Some people put F perp. Some people put FN. I mean, or F perp. Whatever you like. It doesn't matter. Just call it whatever you like. All right. And then there's friction. Friction is opposing motion. So we have friction this way. So F friction. Okay. So that's M1. No, I made a big mistake. You better not make the same mistake. I put weight equals mg. Don't do that. It's m1g. You have to put subscripts. If you don't put subscripts, then you're going to start canceling masses in your equations. And if they're different masses, I mean, you shouldn't cancel them, right? So don't do that, all right? Don't do what I did. Put m1. You're going to be in a lot of trouble if you forget to do that. All right, so we have tension, normal, friction, weight. Now let's do M2. And that's why I usually write this, because it tells my brain there's a subscript, but I forgot. Okay, M2. What are the only forces acting on M2? Well, there's weight, right, and there's tension. So weight, weight's always down, weight, which equals M2G. Now, is the rope pushing it down or pulling it? I mean, what is the rope doing? It's pulling it, right? It's pulling it. So there's tension. Now the nice thing is, as long as you have massless and frictionless pulleys, the magnitude of the tension is the same. So that's a real blessing, right? So whenever you see that massless and frictionless pulley, the tensions are always the same. So, all right. Okay, so here we go. All right, so friction, weight, normal, tension. Tension, weight. Okay, this is accelerating this way, so there's a net force this way. This is accelerating down, so there's a net force that way. Make sure I understand that. And again, the only reason we can say that this T equals this T is because we have massless and frictionless pulley. Later on, we won't have that. We'll have a massive pulley. But then we'll have to have a T1 and a T2 because they're different. Then life gets challenging. So be grateful what we have now. Huh? Okay, one last one. Two blocks are connected by a string. Find the acceleration of each block. Ignore the masses of the string and the pulley. And all, yeah, okay? All right, so pause your video and draw the force diagrams, plural, because there's two objects. Okay, we're back. So we're assuming that this one has more mass than that, so it's going to go like this. Okay, so let's draw the M2. So what are the forces acting on M2? Well, there's the weight, which equals M2G, I didn't forget, and there's a tension up. All right, then for M, and the net force is accelerating this way, so the net force is that way. Now let's do M3. So there's the, all right, now look. Oh yeah, nothing. Oh. So the weight here is M3G, and there's tension. But this time, the net force is this way. Now, by the way, this one, the net force is that way. So which is greater, the tension or the weight? Well, if the net force is greater that way, that means that the tension has to be greater than the weight, right? So here, let's be good for once, right? So that means this magnitude is bigger than this magnitude. Now here, it's accelerating this way. So that means the weight has to be greater than the tension. So let's be good, right? So now the weight is bigger than the tension. All right. There you go. All right, can't say that. All right. Wow, let's see this. I don't know if it's going to work. Actually, watch it on your own, because the volume won't be any good. So make sure you watch this on your own. It's really short. This website is awesome, Minute Physics. They explain things in like a minute. I mean, it's awesome. Okay, what we want to do now is completely shift gears. Now we want to talk about Newton's third law. Now most people can recite Newton's third law, but they have no clue what it really means. So the goal here is to have you totally understand Newton's third law. So this kind of relates to it, right? So basically, the snowball hits the kid, right? Okay, sorry, the kid says, the snowball hit me. What does the snowball say? The snowball says, the kid hit me. And both of those perspectives are correct. The kid hits the snowball hits the kid. The kid exerts a force on the snowball exerts a force on the kid. All right. So let's go back to what we learned earlier. So a force is an interaction between two or more objects. So what we're going to talk about now are the actual interactions. Okay, the interactions. All right. Sully, can you? Yeah, I forgot to tell you. Okay, so I'm going to pull on this bungee cord. So I'm pulling this way. What do you feel? The force pulling what way?
This
No, okay, I'm pulling you this way, but what do you feel?
I feel it stretching.
Yeah, right? Okay, now you pull it this way, and this, so if he pulls this way, okay, but what do you feel?
I feel you pulling that way.
Yeah, okay, got it? Thank you. All right, so when I pulled on the bungee cord this way, you know, he felt the other way. Okay, that wasn't super clear. All right, let's do better. Okay, so watch. Okay, what would the desk say? So just pretend the desk is a human or something, right? So the desk is stationary. Now, what would the desk say just happened to it? The desk would say, you know, here I am minding my own business, and this hand suddenly comes and hits me, exerts a downward force on me, right? And that's correct. Okay, now what we want to do, we want to pretend that the hand is like a person, and we're gonna look at what happened from the perspective of the hand. Now, it's perfectly fine for the hand to say, hey, I'm at rest. Here I am, minding my own business, and suddenly the table comes up and smacks me with an upward going force. Now, we don't usually think it like that, right? We usually assume that the desk is stationary, but again, from the hand's perspective, the hand can think, the hand can say that it's at rest, and the desk came up and hit that. There's nothing wrong with that. Okay, so again, how many slaps are there? There's only one slap, right? There's only one slap. The desk says the force was this way. The hand says the force was this way. There's only one slap, so it has to be true about the magnitude of the forces. Well, the same. It's only one slap. So what we would write that the force hand on table equals, this is magnitude, equals the magnitude of the force table on hand, right? There's one slap, so the magnitude has to be the same. Now, how about the directions? The table says the force was this way, the hand says the force was this way. So the magnitudes are the same, but the forces, the directions are opposite. Okay, this thing, let's see if it's going to work. Come on. Okay. Okay. All right. So watch. So this is a fan, right? Fan. Okay, so look. So if I let go, all right. So what's happening? Well, hold it. So the air, okay, the fan is pushing the air that direction. Agree? So what's the air doing to the fan? That direction. So what do we have? We have the force fan on air equals the force air on fan. And they're equal and opposite, okay? The air was pushing the, well, I just explained it, I don't have to keep saying it. All right, let's do another one. Yeah, me. Okay, I jump up, right? I jump up. Now, when I jump up, the earth pulls down on me, correct? Now, by the way, sorry, let me stop. What we're seeing is that forces always come in pairs. Forces always come in pairs. There's a force hand on table, and there's another member of what's called a force pair, table on hand. There's fan on air and air on fan. So forces always come in pairs. You can't have an unpaired force. It's always like an A on B and a B on A. Okay, so here we go. So I jump up, and I don't go very high. Because the Earth is pulling down on me. So we would say there's the force, Earth on me. Now, forces always come in pairs. What's the other member of the force pair? Well, if there's a force Earth on me, there has to be an equal and opposite force, me on Earth, right? Has to be. That's how it works. Now, here's the fun part. So who has the greatest acceleration, me or the Earth? Well, remember, A equals F over m. So who has the greatest mass, me or the Earth? It's pretty obvious, right? Okay, so what's my acceleration? My acceleration is the force of gravity over my mass, right? I mean, right? Okay, and by the way, what is that? Just 9.8, right? 9.8 meters per second squared, right? Because, come on, let's do it. What's Fg? It's mg, right? What's m? M's cancel, you get g, right? Okay. All right, so my acceleration is 9.8 meters per second squared. Now, what's the acceleration of the Earth? So what's the acceleration of the Earth? Whoa! Well, that's the force, which is, you know, so let's say my weight in newtons is 700 newtons, all right? 700 newtons. It's like, remember, it's mg, right? So it's like 70 kilograms, okay? So let's say my mass is 70 kilograms times 9.8, like 700. I'm just being approximate. But what's the mass of the Earth? 6 times 10 to the 24th kilograms. So therefore, what's the acceleration of the Earth? It's approximately 10 to the minus 22 meters per second squared. Now, what's 10 to the minus 22? Nothing. I mean, it's nothing, right? In fact, I calculated just for fun. It would take about 3 times the age of the universe at this acceleration to go from 0 to 1 meter per second. 3 times the age of the universe. That acceleration is so small, it would take 3 times the age of the universe to go from 0 to 1 meter per second. So, but what am I saying though? I'm saying when I jump up, right, the Earth pulls down on me, correct? But don't I pull up on the Earth? Yeah, I do. I pull up on the Earth. And the forces are the same, right? The forces are the same. But the accelerations are completely different. Because remember, acceleration is F over m, right? So just because you have the same forces doesn't mean you're going to have the same accelerations, you know? And that's all right. Okay, let's see if this thing's going to work now. Okay, so here I have these 2 carts. They have magnets. You can't see them. So I push them together. Okay? So the magnets repel and the carts push away. All right? So which cart pushed which cart? Well, we can say that this cart pushed that, or we can say that one pushed that. But the forces are equal. So I would write something like this. So I would say that F1 on 2 equals negative F2 on 1, right? So there's 2 members of the force of the same force pair. This guy pushes on that guy pushes on that guy, all right? Whoopee! Now, let's put some weight into this guy. I mean, on top of him, and do this. Oh, let go. Okay, what do you notice? Let's do it again. Look really carefully. Hold on. Okay. Come on, be nice. Okay, the forces were equal. Were the accelerations equal? No! This guy went much faster than this guy. And again, no kidding. I mean, it has to be that way because the forces are equal, but acceleration equals F over m. And the masses were different. The forces were the same. The masses were different. So the accelerations are going to be different. How about a collision between a head-on collision between a truck and a small car? What's going to happen? Well, there's only one collision, right? There's only one smack. And so the forces are equal. I mean, let's do it. Again, there's only one smack, there's only one collision, so the force truck on car equals the force car on truck. Okay. But then you say, Brother Weber, you're crazy. The guy in the truck's not going to get hurt. Guys in the car is the one who's going to get killed, right? Well, right. Because the forces are the same, but the accelerations are different, right? Because the mass of the car is really, really small compared to the mass of the truck. So the car is going to have a huge acceleration, right? Let's say it's going this way, then it's going to stop and go that way or whatever. So the car is going to have a large acceleration. The truck is going to have a small acceleration. So that means that the driver of the car is going to have a large acceleration. The driver in the truck is going to have a small acceleration. So that means when the driver in the car smacks the windshield, there's a large acceleration, right? The driver of the truck, you know, he probably won't even smash the windshield because he has a low acceleration. So the reaction, all right, so that's why the guy in the car is going to sustain much more damage than the guy in the truck. All right. Okay. So this is Newton's law of gravity. We'll learn it somewhere along the line. So here's a planet, or it doesn't have to be a planet, it can just be an object. An object of M1, object of M2. This is the center of M2, this is the center of M1. The distance between their centers, we'll learn about that later, center of gravity, later on. Okay, so the force of gravity, which is an attractive force between M1 and M2, is given by that equation. So G is a constant of nature. It's called the gravitational constant, believe it or not. Don't worry about it now. So the force of gravity is G m1 times m2 divided by the distance squared. Okay, great. Now, what is the force that 1 exerts on 2? Well, use the equation. 1 exerts on 2 is just G m1 m2 over r squared. Okay? What's the force that 2 exerts on 1? Well, same thing, right? Same thing. Okay? So this is what we're saying. The forces are an action-reaction pair, or I would say the forces are members of the same force pair. 1 exerts a force on 2, 2 exerts a force on 1, equal and opposite. All right, here's data. So this is something that we're going to use in lab. So this is supposed to be like these are like frictionless carts. This is a track, so they don't move around much. I mean, so they don't wiggle much. All right? And these things are what's called a force sensor. So they measure the forces between them. Okay? And there's magnets and all that. All right. So basically, it's kind of like what I did here, but now we have data. So we push them together. Okay, so we push them together slow. You know, we just push them together. And as they approach each other, there's magnetic repulsion, right? All right, so so this is the force on 1, this is the force on 2. And what do you see? So here they're far apart, then they get closer, the force gets larger, then they move apart, the force decreases. And look at that. What do you notice about the magnitude? It's the same. What do you know about the direction? Opposite. Okay, great. Now here, each cart had the same mass and they were traveling at the same speed. Now we want to change it. Now we're gonna do what I did. So add a bunch of mass to one of them, and shoot them together, you know, slowly, with the same speed. Okay. What do you notice? Same magnitude, opposite direction. Okay. This time, what we want to do. So we're going to keep this one stationary. We're going to put all the extra mass on this guy. I'm going to take this guy and push it that way. Okay? So this guy, all right, so they're going to collide and then they're going to move away from each other. What do you notice? Look at the numbers if you don't believe me, right? Same magnitude, opposite direction. Okay? So Newton's third law is true. All right? So let me just write Newton's third law in the easiest way I can think of. Okay, so so a force is an interaction between two objects. So if there's an A on B, so there's a force that object A exerts on object B. If that exists, there has to be another member of the force pair, which is given by B on A. It's just really simple as that. So the same magnitude, opposite direction. So that's Newton's third law. And, okay, now, does this have anything to do with the masses? Not at all. Nothing. Not at all. Because remember we said this was way more massive than that one, or the Earth and me, or whatever. Has nothing to do with the masses. The forces are going to be equal. The accelerations may or may not be equal. It depends on the masses, right? If the masses are the same, the accelerations will be the same. Okay, so let's just review this and then we'll stop pretty soon. Newton's third law. Every force occurs as one member of an action-reaction pair of forces. The two members of an action-reaction pair act on two different objects, right? No kidding, come on. Here's the object for this one, here's the object for that one. They act on two different objects. This is A on B, this is B on A, two different objects. The two members of an action-reaction pair are equal in magnitude, opposite in direction. Yeah, I already said that. Okay, I don't know, all right? So you got to remember that. People get mixed up. Two members of an action-reaction pair or a force pair act on two different objects. Put that in your brain. Two different objects. Object B, object A. And here's some helpful things. Okay, just reviewing. Forces always come in pairs. If there's an A on B, there has to be a B on A. Forces in a force pair, same magnitude. Opposite directions. Forces in a force pair never act on the same object. B, A. And this is something I didn't tell you yet. Forces in a force pair are always the same type. So like if one is a type of gravity, the other will be type of gravity. If one's electrical, the other force pair will be electrical. You know, they're also the same type. All right. And again, the accelerations may or may not be the same. If the masses are different, the accelerations will certainly be different. All right, let's quit. That one went